Sunflower oil begins as a logistics and separation problem because a harvested load is not pure seed. It's seed mixed with stems, dust, stones, and seeds that vary in oil content depending on variety and weather. The largest factories win on consistency. So the first thing they do is measure and standardize, not crush. Trucks unload into receiving pits, where the load is weighed, sampled, and tagged for traceability. Because oil plants run like refineries, and every lot must be linked to final bottles. Lab checks measure moisture, foreign material, and oil content. Because moisture drives spoilage risk in storage and also reduces extraction efficiency later. If moisture is too high, the plant either dries the seed or blends it with drier lots to hit a safe storage target. Because warm, damp seed can heat internally and generate mold and off-dash odors from receiving. Seed moves through a cleaning train designed to protect machines and protect oil quality. Vibratory screens remove large trash and fines. Aspirators pull off light chaff with controlled airflow. Intestiners separate rocks by density so they don't destroy rolls and screws downstream. Magnets and metal detectors capture ferrous fragments. Because a single bolt can spark in a mill and stop the entire line, clean seed enters. Storage silos that look like grain handling but operate under tighter control. Aeration fans and temperature probes keep the bulk cool and prevent hot spots, and the plant tracks silo temperature profiles, because rising heat is an early warning of moisture migration or microbial activity. Large operations rotate inventory using first out logic because seed age changes free fatty acid levels. And higher free fatty acids mean more refining loss. Before oil can be extracted, the factory has to expose it, and that starts with dehulling for many product specs. Sunflower hulls add fiber, reduce oil yield, and can darken crude oil. So modern plants use impact dehullers that crack the hull without pulverizing the kernel. After cracking, aspiration and gravity tables separate light hulls from heavier kernels. And separation efficiency is monitored because lost kernels in the hull stream are lost profit. Hulls aren't waste. They become boiler fuel or pelletized biomass, and that energy loop often powers steam generation in the same facility. Next comes size reduction, because extraction depends on surface area and cell rupture. Cracking rolls break kernels into smaller pieces, then flaking mills compress them into thin flakes. Flake thickness is a critical control variable. Too thick and solvent can't penetrate efficiently. Too thin, and the material becomes powdery, creating channeling and fines that clog extractors. Inline gap sensors and motor load monitoring keep flakers producing a consistent thickness at high throughput. Conditioning follows, and it's where the plant uses heat and moisture as process tools. Conditioners gently warm the flakes to adjust viscosity and soften cell structures, improving oil release during pressing. This heating is controlled to avoid damaging the oil. Excessive temperature accelerates oxidation and raises refining load later. Steam jackets and indirect heaters maintain precise temperatures, and residence time is tuned so heat is uniform through the mass. Not just on the surface. Now the line reaches the mechanical extraction step, pressing. Continuous screw presses apply, increasing pressure as material moves through a narrowing barrel, forcing oil out through slotted cages while doiled solids exit as press cake. Press settings are engineered around throughput, residual oil in cake, and temperature rise from friction. Higher pressure and tighter choke increase oil recovery, but also raise temperature and wear. So plants balance press performance against energy use and maintenance intervals. In the largest factories, pressing is usually not the end. It's the first stage of a two-stage extraction system. Pressing removes a large fraction of the oil quickly and reduces the load on solvent extraction, which is where the last few percent of oil is recovered economically. That last few percent matters because, at megascale, a 1% improvement in residual oil translates into massive annual yield. The press oil leaving the screws is crude and carries fine solids called foots. It flows through settling tanks and centrifuges that spin out suspended particles. Because solids accelerate oxidation and create deposits in heat exchangers. The plant monitors turbidity and insoluble content to keep crude oil clean enough for refining without excessive Filtration loss. The press cake heads to solvent extraction, and this section of the plant resembles a chemical refinery. The cake is conveyed into a continuous extractor, often a loop belt, or rotary cell design, where it is washed with food-grade hexane. Hexane is used because it dissolves oil efficiently and boils at a manageable temperature for recovery. The extractor is engineered for counter-current flow. The freshest solvent contacts the most depleted solids, and the most oil-rich solvent contacts the freshest cake. Maximizing driving force and minimizing solvent use, inside the extractor, mass transfer is the real work. Solvent must wet the solids, penetrate the porous structure, dissolve oil, and carry it out as micellar, which is a mixture of hexane and oil. Bed depth, percolation rate, and temperature determine extraction efficiency. And plants monitor these with flow meters, temperature sensors, and sometimes density signals on the micellar stream. Channeling is a constant risk. If solvent finds easy paths, parts of the bed remain unwashed and oil stays trapped. So extractor internals and feed distribution are designed to keep flow uniform. Once micellar leaves the extractor, it goes to distillation to separate oil from solvent. Multi-stage evaporators remove most hexane under controlled heat. And final stripping uses vacuum and steam to drive residual solvent down to extremely low levels. Solvent recovery is not just economics, it's safety and compliance, so the distillation system is sealed, monitored, and integrated with vapor recovery. Condensers capture hexane vapor and return it to the solvent loop. And leak detection systems constantly check for vapor presence, because hexane is flammable and must be contained. The extracted solids, now called meal, still hold hexane and must be they pass through a dissolventizer toaster dryer cooler, a tall vessel where indirect heat and steam strip out solvent, toast the meal to improve stability, and adjust moisture to a safe level for storage. This unit is engineered to recover solvent vapor efficiently while controlling meal temperature, so protein quality meets animal feed specifications. The meal becomes a major byproduct stream and a key revenue component, so plants track residual oil, protein, and moisture continuously. Now the plant has crude sunflower oil from both press and solvent roots. And crude oil is not ready to drink or cook with. It contains phospholipids, free fatty acids, pigments, waxes, and odor compounds. And refining is the process that removes those while preserving desirable nutrients and flavor. Neutrality. The first refining step is degumming. Designed to remove phospholipids that cause haze and poor stability, water degumming adds controlled water to hydrate gums so they separate, while acid degumming uses small amounts of food-grade acid to convert non-hydratable phospholipids into removable forms. High-speed centrifuges then separate gums from oil, and the plant controls temperature and mixing intensity because poor hydration leaves gums in the oil, creating downstream fouling and yield loss. Next is neutralization, where free fatty acids are removed to improve taste and stability. In chemical refining, caustic soda reacts with free fatty acids to form soap stock, which is separated by centrifuge. The dosage is calculated from lab-measured acidity, because underdosing leaves acids that reduce shelf life, while overdosing creates excess soap stock and carries away neutral oil and emulsions. Many large plants use physical refining for certain oil specs, reducing caustic use and wastewater. But that requires tight upstream degumming, because phospholipids must be low before. Physical deodorization can work efficiently after neutralization. Washing and drying remove residual soaps and water. Vacuum dryers and heat exchangers bring moisture down because water promotes hydrolysis and oxidation during storage. Moisture measurement is continuous, because even a fraction of a percent can affect stability and cause cloudiness in bottled oil. Bleaching is next, and it's a controlled adsorption process, not a dye step. Activated bleaching earth and sometimes activated carbon are mixed into warm oil under vacuum to remove pigments like chlorophyll and carotenoids, as well as trace metals that catalyze oxidation. Contact time, temperature, and dosage are optimized because too little leaves color and instability, while too much increases oil loss in spent clay. After adsorption, the oil passes through pressure leaf filters that trap the spent bleaching earth. And differential pressure across filters is monitored because filter blinding can choke throughput. Deodorization is the step that makes sunflower oil neutral, and it's a high-temperature, high-vacuum steam stripping operation. In a deodorizer, the oil is heated under deep vacuum and contacted with sparging steam, which carries off volatile compounds responsible for odor and taste. Temperature, vacuum level, steam rate, and residence time are validated parameters because deodorization also reduces contaminants and can improve sensory quality. But overprocessing can strip desirable minor compounds and increase thermal degradation. Modern plants use heat recovery aggressively here. Hot deodorized oil preheats incoming oil through economizers, cutting energy per ton. Sunflower oil also contains waxes that can cause cloudiness, especially in refrigerated conditions. So many factories add winterization, also called dewaxing. The oil is cooled in a controlled way, so wax crystals form at a predictable size, then held in crystallization tanks long enough for crystals to grow. Filtration systems remove the waxes, producing a clear oil that stays bright in the bottle. Cooling rate matters because rapid cooling forms very fine crystals that are hard to filter, while slow, controlled cooling produces filterable crystals and higher throughput. At this point, the plant may also tailor the product by blending or fractionation. High oleic sunflower oil is often produced from specific sunflower varieties, and the factory maintains segregation because the fatty acid profile is the product. Blending can standardize taste, stability, and performance for frying, while maintaining labeling requirements. Every blend is verified with lab analysis of fatty acid composition, peroxide value, anicidin value, and color, because large customers require specifications, not promises. Throughout refining, Oxidation control is constant. Oxygen exposure is minimized by closed piping, nitrogen blanketing in tanks, and vacuum operations where possible. Antioxidants may be added if permitted and desired, but premium oils often rely on low oxygen handling and tight process control instead. Storage tanks are stainless or lined and designed to avoid dead zones where oil can stagnate and degrade. Now the process shifts from refining to packaging, and this is where a mega factory turns bulk oil into retail units at extreme speed. Bottles arrive on pallets and are depalletized automatically. Air rinsers remove dust, and conveyors feed bottles into high-speed rotary fillers. Filling is typically volumetric with mass flow verification. Because net content compliance is critical and oil viscosity changes slightly with temperature, caps are applied with torque control, because too loose leaks and too tight distort seals. For flexible packaging in bulk formats, the plant fills bag-and-box drums, or totes using metered filling heads, and nitrogen purge to reduce oxygen in headspace. Headspace oxygen is not a small detail. It predicts shelf life and flavor stability months later. Many lines use inline oxygen analyzers and reject units that exceed limits. Every packaged unit passes through inspection. Checkweighers verify fill weight. Vision systems confirm label placement and date codes. And case packers and palletizers stack product with consistent geometry for warehouse stability. Traceability codes link each bottle back to the refining batch, which links back to the seed lots, which is how a plant can isolate issues fast if a customer reports a defect. Quality assurance never stops, because edible oils fail in predictable ways. Free fatty acids indicate hydrolysis or poor raw material. Peroxide value indicates early oxidation. An aceton value indicates secondary oxidation and stale flavors. Color measurements catch pigment carryover. Sensory panels detect flavor drift that instruments might miss. If the plant produces frying oils, it also monitors polymer formation tendency and smoke point performance. Because commercial kitchens punish oil harder than home use, the largest factories also run as energy systems. Pressing generates heat, refining uses steam, distillation recovers solvent, and deodorization offers major heat recovery opportunities. Many plants burn sunflower hulls to generate steam, turning a low-value byproduct into process energy and reducing reliance on fossil fuels. Variable frequency drives on fans and pumps match power draw to load, which matters because oil plants run continuously and small. Efficiency gains compound over months. Safety engineering is especially intense in the solvent extraction area. Hexane systems operate under explosion-proof standards. With inerting gas monitoring and strict control of ignition sources, ventilation, grounding, and static control are engineered into floors, conveyors, and filters, because fine organic dust and solvent vapor are a dangerous combination if design is sloppy. Shutdown systems are automated. Operators train for upset conditions because a safe plant is a productive plant. Waste and byproducts are managed as products, not disposal. Soap stock from neutralization can be acidulated to recover fatty acids for industrial uses. Spent bleaching earth is handled as an oily waste with controlled storage to prevent spontaneous heating. Wastewater from washing stages is treated to remove oils and reduce cod before discharge, often using dissolved air flotation and biological treatment. The economics of a mega factory depend on turning as many side streams as possible into value streams. What looks like a simple bottle of sunflower oil is the output of a tightly controlled chain. Mechanical cleaning to protect equipment, precision dehulling and flaking to expose oil, pressing and solvent extraction to recover nearly every drop, and multi-stage refining to remove gums, acids, pigments, odors, and waxes without damaging the oil. At the largest scale, the amazing part is not the sunflower. It's the process control that lets a biological crop become a standardized, shelf-stable cooking oil produced continuously, measured constantly, and shipped by the millions of bottles with the same clarity, flavor neutrality, and performance every time.